Hello, welcome to video 32 in the lecture Advanced Mathematic Modeling. So in the last example I showed you a random walk with a short-term memory, and so this led to diffusive behavior after a transient. Now we want to enter examples where we find non-diffusive behavior of walkers, and to introduce this I start with something where we're still in a diffusive range, but to show you how you can combine different types of random walks or movement in different dimensions. So we look at the example of a smoke plume from a chimney. So okay, let's assume you have here a chimney, and here comes smoke out of this, and then the smoke is going upwards because it's warm air going upwards in the atmosphere, and but then it's also the molecules, the smoke molecules are moving, doing a random walk, are diffusing left and right, and so we find a broadening of the plume. Okay, now of course it depends now. We're interested in the form of the plume that we can see here. Now it depends. If you have a wind blowing, then of course the smoke is just affected to the side. But if there is no wind, let's assume there's no wind, and I don't know if you know this, like then typically we see here a parabolic shape of the smoke which is going out of here, the chimney. And so let's do a model for this. We model this in just in 2 dimensions. And so assume we have now a motion in a 2-dimensional lattice. We have here a y coordinate and an x coordinate. Here we start here. So at 0, that's the point where our molecules are entering. So directly it's here at 0 where the molecules are entering our system. And now we combine 2 kinds of motions. So in the vertical direction, in the y direction, so vertically, so we assume we have a constant velocity, so we have here a particle of a walker, and the walker can now in this let's keep it the lattice. We could also do it continuous, but let's keep it the lattice. So we have here, so the walker is our smoke molecule which entered the system here at this position, and now at every time step the smoke just goes 1 position higher. So we have a constant velocity upwards, v0, and so we know that y as a function of t will be 0 times t. So we have here ballistic movement upwards. So now in x direction, we say our molecules make a simple random walk, unbiased, uncorrelated random walk. So horizontally, we have an unbiased, uncorrelated random walk, And in the simplest case, that we jump just one position left or right. So this means the walker in the next step will go one level higher, and then with equal probability goes left or right. For example, it goes here. Then it goes again one level higher with equal probability left or right. Maybe it went here, then it went there, it went there, and so on. So that could have been one trajectory of the walker. But the walker in a different realization, the walker maybe would have gone here, maybe there, 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 there. Yeah. And so we would have a walk here. And now you can have many realizations. So in every step the walker goes one level higher in y direction and randomly a step in left or right direction. Yeah. And now the question is, what's the probability distribution of the walker if you have many molecules of walker which start here at this point? Yeah. But we know for the unbiased random correlated random walk, so the typical distance that the walker can do in x direction goes with the square root of t. Yeah. And then you see, if you know you want to know the shape of the profile, you want to know, so on average, how fast did the walker come when it has how far in x direction did the walker or the molecule come when it has a certain height. So we need now the function y as a function of x, and then you see y as a function of x, so y goes proportional to t, x goes with square root of t, and then you see y of x goes proportionally to x squared. And so we get a parabolic shape. Of the smoke plume. Yeah. Of course, now if you would have a wind, then you would have a bias direction in a certain to left or right, and we would have a biased random walk, and then the whole plume would be moved to the side. Okay, so that would be too simple, the exercise, or for what we're interested, because basically that's all stuff we know already, but it just shows you if you combine different walks, types of walks in different dimensions, you can have a certain characteristic shapes. And here, so we find then a power law relationship, at least, so we see because like here y and x coordinates on average will be related by a power law, and this is an analysis. This goes back to Taylor, who analyzed this example when you have here also some correlations, some short-term correlations. But now for the point of this process, for this lecture, now we want to go to a different example, which is a slight twist. Yeah? And this is the model by Matheron and de Marsiliy. And now we have something similar. We have a walker in such a two-dimensional layer, lattice, but in this case we don't have smoke, we have pollutants in the groundwater. So we say we have again a vertical layer. Now we're in the ground. That was in the air. We're in the ground. we have the x position and the y position, and now we assume, now we have real layers. So here this lattice was just a lattice for construction to make a simple random walk. If, for example, you would like to do this in the computer, but essentially in the left example, this was a continuous process. But now we assume we have here real layers in the y direction. Yeah? And so now in each layer we have a certain velocity of the water flow. So we have pollutants in the groundwater, and they are attracted by water. By groundwater. And now we need to say something what how the groundwater goes in the model. And so we say now, so we have a velocity now in the y direction and in the x direction, vx here. And now we assume this depends on the layer. Yeah. So maybe in this layer the groundwater goes to the right, maybe in this layer the groundwater goes to the left, maybe again to the left, maybe to the right, whatever. So in every layer we have a constant velocity, and that's the velocity of the groundwater. And that's an assumption these authors did in the model, which is also realistic in certain kind of sediments. So like that you have different layers, and the groundwater can be in a different layer. Yeah? And so for the sake of this model, we assume now this velocity is frozen disorder. So we assume in every layer the horizontal velocity is a random number, but it doesn't change in time, so it's frozen. Yeah? And in the simplest case, it's just it's totally independent from the others, and we just go left and right with a certain probability. And of course, we assume it's unbiased here, so going left or right has the same probability. So, and now we start again with a pollutant. Now it can start somewhere in the middle. It's in a layer. The pollutant will always be in a layer. And for example, this guy, we will move to the right with constant velocity. Now we have to say, what does our pollutant do in the vertical direction? And here we say in the vertical direction is doing a random walk. So meaning, in contrast to this model, the chimney, where the smoke molecules always just went upward. Yeah. Now here our pollutant in the water makes a random walk. It goes up and down randomly. But in every layer it will horizontally go depending on the velocity of its layer. Yeah. So it's again, so then now you can see what's happening. So like this guy will move to the right, and maybe he a certain distance, but then maybe he goes a step upwards, then maybe so he would end up here. But then maybe here we go again to the right, maybe he goes down again, because he goes randomly up and down. Now he's here again, he goes again to the right, but now maybe he went again down, then he's here. Now he goes to the left, maybe he went down again, then he would be here. Yeah, and now you can think how what's happening. So the walker will then go up again, also with certain probabilities, might go up again, then it moves again to the right, and then you find some kind of behavior here. And the question is now, in this kind of random walk, where the walker is doing a random walk up and down, and basically also a random walk left and right, but the random walk left and right is in a frozen disorder. What does these combinations will do for the horizontal displacement? Because like in the vertical displacement, it's very clear, it's just diffusion, because in the vertical, the vertical movement is totally independent from the horizontal in this model. So the vertical movement is just random. Yeah, but the horizontal movement always depends on the vertical position. So the horizontal movement is coupled on the diffusive movement in a y direction. And now let's see how can we calculate what's happening. And so we need to calculate some correlation, some movements to covariance functions for the movement horizontally. Yeah, and then it's clear, if we know that the particle, if it's in the same layer, then the horizontal movements will be correlated, because then they always go in the same direction. Yeah, if the particle is in different layers, then the horizontal movements will be non-correlated, because we don't know if the movement in the layer goes left or right. So in order to have the autocovariance function, we need to know the probability that the walker is in the same layer, so the same y layer, same vertical layer, at time t0 and another time t1. Yeah. And so, like, what's the chance that the walker vertically has returned to the same layer? Yeah. And if we start with if we say t0 is 0, so we start with a certain layer, and then we ask, what's the probability that the walker at a certain time has approached a layer? So now, in order to get this probability, we make a hand-waving argument. So we could say, let's say, so that's the time, and that's the position, the vertical position of the walker, and we know on average the walker will increase here. The average position goes with square root of time. Yeah. So this means after the square root of time, the walker has done this displacement. Now, what's the probability that he is still at the same position, that he ended up again in the same layer here? Yeah? This will be more and more unlikely the larger he was starting to be separated from 0. Yeah? So the probability to be still here, you can assume that this probability p goes proportional to 1 over square root of t1 minus t0. Yeah? Because the walker in a certain delta time advances on average with the square root of the time difference, and so the probability to be in the same layer goes with 1 over the square root of this time difference. And this means, but if the walker is in the same layer again, then this autocovariance function after a certain time difference, yeah, will be 1 if the walker is in the same layer, because if it's in the same layer as a certain time delta t before, he will be advected in the same direction. So basically this means, so this goes with 1 over this I minus j. Yeah. So here we find an autocorrelation function which decays not exponentially, but decays as a power law. So, and this is as a power law of the time difference. So our c of k, which of the time difference k, which before in the short-term memory was an exponential function, now decays with the power law. And now we want to know what's the typical horizontal position as a function of t. And then we need to calculate our correlation sum. And let's assume we have continuous time. So we integrate from 0 to t over dt1. And then we integrate from 0 to t1 over dt2. And we have to sum over this correlation integral. Basically, we have to integrate over t2. Oh, sorry, I always forget to shift this. t2 minus t1. Yeah. And so if we integrate this, now this is just an integral we can calculate. Yeah. And so you will see this goes with t to power 3 over 2. So this means here we have a behavior where the mean square displacement, so the second moment as a function of time, doesn't go linearly with t, but t to an exponent which is larger than 1. So we see that the typical position of the walker goes proportional to t to an exponent alpha, and alpha equals 3 over 2. This means if we have this combination of random walks, normal random walk in y direction, but then depending on every y level movement left or right with this frozen disorder, the horizontal movement goes with the power law. And that's because this correlation, so the chance to be in the same layer again, decays as the square root of time. And so we have here an example of a horizontal displacement which doesn't follow a diffusion, and we call something like this, where we have here an exponent which is larger than 1. So this walker is increasing on average, so the pollutant is increasing on average faster than a random walk, but slower than just the horizontal, as if it would stay in the same layer and would go ballistic. It's somewhere in between. So if this alpha is larger 1, we have a super diffusive behavior. Super diffusion. And this is our first example for super diffusion. So I agree that this example was very fast, but this model will also be one of the exercises, so this Matheron-de-Marsiliy model, where you just try to simulate this process in the computer and then calculate the position of the pollutant or the walker if you so want, and then you can now look what's the mean square displacement, and then you plot the mean square displacement in a log-log plot, and then you will see that we suddenly see super diffusion in a system where nothing looks suspicious here. So at first guess we would have thought, I mean, since x and y directions are random, and the position of the walker is also random, so we would assume that also horizontally we would have a diffusion. But since the walker here, when he starts vertically to move, when it by chance enters the same layer it had before, he is advected in the same direction. So this gives a long-term memory, because like if he was in a certain layer, he was advected in a certain direction, yeah, and then he is doing his random walk, and after a long time he comes back in the same layer. The memory is still there that first he was advected in a certain direction. So there's really a long-term memory in the horizontal movement. So that's a good example to wrap your brain around and try to understand what's going on, to see that suddenly here we have this super diffusive behavior, and it's maybe very good to have something like these alternatives, for example this, where the movement is always just vertically, or you could have different example where you go randomly, just a random walk and up, left and right, so upward, vertically or horizontally, always randomly without a frozen disorder. So this means the water ground velocity would just every time instance be random. Then you would also have a random movement in the x direction, or a diffusive movement in the x direction. And we can do one step more. For example, what would happen if we have something like this, if we're in a movement in a shear flow? Let's assume we have again our pollutant moving in our water field. But now assume that so it can go in y direction, in x direction, and now we want to see what's the velocity of the x direction. And now it's not random, it's still frozen, but it depends systematically on the y direction. And assume in the middle we have no flow at all horizontally, so the Vx, the horizontal velocity, is 0 and increases here and decreases, so it goes to the right. And then in the top layer, then it goes, the velocity is decreasing, the velocity is 0 in the middle, and then the velocity goes to the left in the lower layers. So this would be a shear flow, which happens very often, you know, when you have two moving boundaries. So in the top layer, the movement goes to the right. In the lower layer, the movement goes to the left, and then the water in the middle has to have some intermediate movement. And now let's assume we have a shear flow, but in vertical direction we are again moving randomly. So now the question, what's the displacement in x direction? This is something we have not planned as an exercise, but it's very easy for you to take your numerics and try to figure out what's happening in x direction. Or we could change this velocity profile, and for example, what would happen in this kind of profile? So we have again our two-dimensional walk. In the y direction we go randomly, random walk in y direction. We have again a higher and lower level. And now let's assume the profile of our shear flow is differently. So our x component of the horizontal velocity is not decaying linearly, but in the top layer we always go to the right with the same velocity, and in the lower layer we go to the left with the same velocity. So here we had a vertical profile like this, and now we have a vertical profile of the horizontal velocities, which is a step function. Yeah? And now we want to know again what's the displacement in x direction. And here again you will see with these models we find a non-diffusive behavior. So in y direction our walker is going up and down. Yeah? So and now it depends, during the random walk, is our walker in the positive part or in the negative part? And as long as it is in the positive part, the walker will always go to the right. As soon as he crosses in the negative y values, he goes to the left. And now it depends, the question, how long does a random walker be has a positive value, and how long does a random walker has a negative value? And now when you combine this, and then you see in x direction, you will find something which is a levy walk, which is also super diffusive. And if you want to see this, just make the simulations in the computer. Again, very easy, and check the displacement in x direction. So this were just some examples from a combination of horizontal and vertical movements, which are maybe one of the simplest models to show super diffusion. But we will see a lot of more examples in later lectures, and also these levy walks, we will have a closer look to them, but not in such a system, but in a system where we directly find a levy walk. But this we will see in the next lectures. For the moment, I showed you, I hope I showed you that there is simple models where the diffusion is not diffusive, and okay, you could now say, okay, this maybe are constructed examples, maybe only some groundwater geologist would be interested in them. Why should I be interested in this kind of things? But these are just first examples, and I want to make the point during the lecture that this kind of super diffusive behavior is just this kind of behavior where things get really interesting. Okay, thanks.